Our brains are incredible. They are complex networks of billions of neurons. These neurons communicate with each other through electrical and chemical signals. This intricate web allows us to learn, think, and experience the world around us. The human brain is the inspiration for artificial neural networks. We marvel at its abilities. Scientists and engineers want to replicate its power. Artificial neural networks aim to mimic the brain's learning process. They use interconnected nodes or artificial neurons to process information. Like their biological counterparts, these artificial neurons receive, process, and transmit signals. The connections between neurons, called weights, determine the strength of these signals. By adjusting these weights, artificial neural networks can learn from data. This learning process is at the heart of artificial intelligence. The human brain is still far more complex than any artificial neural network. Yet the progress in this field is remarkable. We are unlocking the secrets of the brain. We are using this knowledge to create intelligent machines. This journey takes us deeper into the fascinating world of deep learning and its applications. Imagine a group of friends playing a game of telephone. Each person whispers a message to the next, and the message changes slightly with each whisper. Finally, the last person announces the message, which may be quite different from the original. This resembles how an artificial neural network works. Information flows through layers of interconnected nodes. Each node performs a calculation and passes the result to the next layer. Connections have weights that determine signal strength. These weights adjust during learning, improving accuracy. Just like we learn from experience, neural networks learn from data. By feeding labeled examples, the network adjusts to produce the desired output. This process is called training. From recognizing faces to translating languages, neural networks are transforming fields. Deep learning takes artificial neural networks to the next level. Imagine a neural network with many hidden layers between the input and output layers. This is the essence of deep learning. These hidden layers allow the network to learn complex patterns and representations from vast amounts of data. Think of it like this. Each layer of the network learns to extract different features from the input data. The first layer might detect simple edges or colors, while deeper layers learn to recognize more complex shapes, textures, and patterns. This hierarchical learning process is what makes deep learning so powerful. But how does the network know how to adjust its weights to improve its performance? This is where backpropagation comes in. This algorithm calculates the error between the network's output and the desired output. It then propagates this error back through the network. The weights are adjusted to minimize the error in future predictions. Deep learning has revolutionized areas like computer vision, natural language processing, and speech recognition. It's powering the development of self-driving cars, virtual assistants, and medical diagnosis tools. The possibilities are truly astounding. Remember the days of blurry scanned photos and struggling to identify objects within them? Today our smartphones can instantly recognize faces, places, and even specific dog breeds in photographs. This remarkable progress is largely due to the power of convolutional neural networks. Convolutional neural networks are a specialized type of deep learning architecture designed specifically for image recognition tasks. They employ a unique technique called convolution, which involves sliding a small filter over the input image to extract features. These features are then passed through multiple layers, each learning to recognize increasingly complex patterns. The beauty of convolutional neural networks lies in their ability to learn hierarchical representations of images. Early layers might detect edges, corners, and simple shapes, while deeper layers learn to recognize more complex features like eyes, noses, and eventually entire faces. This hierarchical feature extraction allows convolutional neural networks to achieve exceptional accuracy in image classification, object detection, and image segmentation tasks. From unlocking our phones with Face ID to assisting doctors in diagnosing diseases from medical images, convolutional neural networks are transforming the way we interact with the visual world. Section 5. Self-driving cars navigating with neural networks. The dream of self-driving cars, once confined to science fiction, is rapidly becoming a reality. At the heart of these autonomous vehicles lies a complex interplay of sensors, algorithms, and of course, neural networks. Neural networks play a crucial role in enabling self-driving cars to perceive and navigate their surroundings. Using data from cameras, LiDAR, radar, and GPS sensors, These networks can identify obstacles, interpret traffic signals, predict pedestrian movements, and make real-time driving decisions. One of the key challenges in autonomous driving is object detection and tracking. This involves identifying objects in the car's vicinity, such as other vehicles, pedestrians, cyclists, and obstacles. CNNs excel at this task, providing the car with a detailed understanding of its surroundings. Another crucial aspect is path planning. RNNs, which we'll discuss in the next section, are particularly well suited for predicting the future trajectories of moving objects. This allows the car to anticipate potential hazards and plan a safe and efficient route. Section 6. Building a perceptron, a simple neural network. Let's build a simple neural network called a perceptron. Imagine a neuron receiving two inputs, x1 and x2, each with a weight, w1 and w2. It multiplies each input by its weight, sums the results, and applies an activation function. The activation function introduces nonlinearity. For example, it can decide whether to wear a jacket based on temperature and chance of rain. During training, it adjusts weights to minimize prediction errors. The perceptron forms the foundation for more complex neural networks. Section 7. Learning from mistakes, backpropagation and optimization. We've talked about neural networks learning from data, but how exactly does this learning process occur? The answer lies in a powerful algorithm called backpropagation. Imagine you're playing darts and your first throw lands far from the bullseye. You observe the error, adjust your aim, and throw again. Backpropagation works similarly, but instead of adjusting your aim, it adjusts the weights of the neural network. When a neural network makes a prediction, backpropagation calculates the error between the predicted output and the actual output. This error is then propagated back through the network, layer by layer. At each layer, the algorithm calculates how much each weight contributed to the error and adjusts the weights accordingly. This process of calculating the error and adjusting the weights is repeated for every example in the training data. Over time, the network becomes better at making accurate predictions. To further enhance the learning process, we use optimization algorithms. These algorithms determine how the weights should be adjusted based on the calculated error. Popular optimization algorithms include gradient descent, stochastic gradient descent, and ADAM. Section 8. Convolutional neural networks, mastering image data. We've already touched upon the power of convolutional neural networks, or CNNs, in image recognition. Let's delve deeper into their unique architecture and understand why they're so effective at processing visual information. Unlike traditional neural networks that treat each input pixel independently, CNNs exploit the spatial relationships between pixels. They employ a technique called convolution, which involves sliding a small filter or kernel over the input image. This filter extracts features from local regions of the image, such as edges, corners, and textures. These extracted features are then passed through a pooling layer, which reduces the dimensionality of the data while preserving important information. This process of convolution and pooling is repeated multiple times, with each layer learning to recognize increasingly complex patterns. The final layers of a CNN are typically fully connected layers, similar to those found in traditional neural networks. These layers combine the features learned by the convolutional layers and make predictions based on the extracted information. CNNs have revolutionized computer vision tasks, achieving human-level or even superhuman performance in areas like image classification, object detection, and image segmentation. Section 9. Recurrent neural networks, remembering the past. Imagine trying to predict the next word in a sentence. You wouldn't just consider the current word, but also the words that came before it. Context is crucial for understanding language, and that's where recurrent neural networks, or RNNs, shine. RNNs have feedback loops that allow them to retain information from previous inputs. This memory enables them to understand sequences of data, such as text and speech. LSTMs were developed to overcome the vanishing gradient problem. They are ideal for tasks like language translation, speech recognition, and video analysis. Conclusion. From the humble beginnings of the perceptron to the sophisticated architectures of CNNs, RNNs, and LSTMs, neural networks and deep learning have come a long way. Inspired by the intricate workings of the human brain, We continue to unlock the secrets of intelligence and build machines that can see, hear, understand, and even think. As we delve deeper into the realm of deep learning, we're not just building intelligent machines, we're expanding our understanding of the universe and our place within it. The future of artificial intelligence is bright, and the journey has just begun.